I was supposed to be the first speaker, but missed my turn somehow. So I would like to start with thanking the organizers for the opportunity to participate in this summer school and for putting together a very interesting set of tutorials. I'm a student, grad student at Liquid Crystal Institute at Kent State University, working with Peter Palfy, and I would like to talk today about probing liquid crystal elastomer structure with polarized light scattering. We've heard few interesting lectures already, so I'll hope I'll be able to contribute maybe a little to what's been said before. And I would like to acknowledge also people who were involved in this research, and that would be Christopher Grabowski and Paul Lucetta. Well, I guess the first thing I should start is from the picture what a liquid crystal elastomer is, and that's essentially a system of cross-linked polymer network with some mesogenic units attached to it, and they can be, well, imagined to be attached as a side element to the main chain, or to be incorporated in the main chain altogether. And then this all happens at molecular scale, and then since it's a liquid crystal, these small guys can align and form pneumatic phases, and then the orientation can be described with a thing which is called a director. And so it happens that that director can be nicely aligned macroscopically, or, well, not so much nicely aligned. And this kind of alignment is usually called as a monodomain elastomer, and random orientation is usually called polydomain. And again, it happens so that variation of the director in elastomer often occurs at the length scales of microns, so that can be seen with light. And light scattering can be, well, used as a technique to probe some structure of the elastomers. And these are a few typical scattering pictures from the elastomers, where I'm pressing the wrong button all the time. Sorry for that. So the left one is the scattering from polydomain liquid crystal. It is isotropic, and well, basically we can say that there is some maximum length scale in this picture. And for those who are not familiar with scattering, basically the distance from the center of the picture tells us the further the distance from the center, the smaller is the length scale of variation in our system. And then if the system is very nicely aligned and has no spatial variations, we would have no scattering at all. So this second one, well, I'll say about the third one. So this third one is the scattering pattern from quite well-aligned elastomer, and this in the middle one, again, is something between the polydomain and monodomain. And from these pictures, we can say that there are some length scales that are observed in our system, and usually, so these peaks correspond to few micron variation. So, also known thing that the alignment of the director in elastomers is coupled with a strain, and that is an interesting fact, and a lot of things are done with that, but that's just to mention. And this effect can be, well, this effect, right? This thing can be done with already fully cross-linked polymers, elastomers, and then when they are stretched, the alignment increases. When they are released, they contract back to the original state, and alignment goes goes to original disordered or partially ordered system. But then a typical way to prepare elastomer is a Finkelman's two-step process, where first a swollen gel partially cross-linked elastomer is prepared, and then it is the cross-linking is finalized under some strain, and that strain promotes alignment during the final cross-linking process, and at the end one can get a nicely aligned elastomer. So I have to also mention that there's been previously experiments looking at the scattering of light in elastomers during their transition from polydomain to monodomain state in the fully prepared cross-linked elastomers. What I would like to show you here is the results of monitoring the process of deswelling of the partially cross-linked elastomer. So what is described here is what happens with the structure of the elastomer when it's being deswelled and either stretch or not stretch at the same time, and thus either undergo a transition to monodomain state or polydomain state. So these pictures were taken by Chris Grabowski some time ago, and the top line is the time evolution of scattering pattern from the sample which is not subject to any strain during the deswelling. And what happens here is that in the at first the transition from isotropic to nematic state occurs, and then due to the weight of elastomer itself, the symmetry breaks, and some spatial component is preferred, and liquid crystal phase happens at that scale. And then when the cross-linking continues, the gravity effects are negligible, and at the end the nice uniform scattering pattern is obtained. If one stretches the film during the evaporation, that keeps the symmetry broken, and at the end the sample, the sample that we make becomes quite nicely aligned, and this is illustrated in this set of pictures. And I think I'm not doing it fast enough. So, so we have these experimental results. I guess this is my phone. So, but we don't really know what is happening with the structure of the elastomer inside, either during this process or just during stretching. So we would like to know that, and for that we want to do some simulations. And again, simulating scattering process is quite hard, so I'll just try to come up with some the simplest system that I can come up with to produce scattering patterns which would look like this, essentially, with this fourfold symmetry, and that would give some reasonable configuration of the director. So what assumptions do we do for the elastomer? I'll have to mention here one more thing, that there are two ways to approach this model. We can say that we would specify some sort of interaction or internal mechanism of interaction within the elastomer, and then simulate how that thing evolves. Or we can just say we don't really know what's happening inside, and we'll try to guess, well, after all, to guess the director configuration which would give us the scattering pattern that we got. And this is easier, I guess. So I'll try to tell you a little about this approach. what we're gonna do, or what we assume for our elastomer film, we'll say that it's plane, it's only one layer film. We'll say that it's in XY plane, and then it's uniform along Z. And then we'll also fix the director in the plane of the sample, and we'll allow it to vary also only in the plane of the sample. And also what we know from observation and from common sense, that at the end, at least, of the stretching of the alignment, it is quite well aligned, so we don't expect to have any defects there. And then also, as a even stronger requirement, I'll say that the orientation or deviation of the angle from the average direction should not be bigger than pi by 2. So basically, it doesn't twist around. So these are the assumptions. Now, to do the light propagation, we just assume that the incident light is linearly polarized. Then calculate the light propagation through the elastomer sample, and one could use a bunch of methods for that. And well, again, I guess the simplest one is the Jones one. And then the exit plane of the sample can be treated just as a set of point light sources. And to calculate the light scattering pattern on the screen, we just have to sum the light. For every point on the screen, we have to sum the light from every point on the exit plane of the elastomer. And that's the recipe, essentially. So now the question is, what kind of director should we choose? And that's not a very trivial question, because again, what we know is that the system should be somewhat random. At the same time, we know that there should be some spatial length of variation captured in that in that random pattern. And also, we can assume, at least for some cases, that the variation of the director is smooth. So the idea then would be, well, let's try to approximate it with a Fourier series. And then again, it would be then fully defined by the magnitudes of every component, and then the phase shifts of every component. So I guess I have only a few minutes left. So, 2. All right. All right. So now, if we say that this phase for every component, and this is quite important thing here. If we say that this phase is the same for all the spatial frequencies, we will not get the uniform or randomly uniform pattern of the director, and that can be illustrated in one-dimensional case. So here, this is just a sum of 20 first terms of a Fourier series along X, and this one is when the phase, the extra phase shift is 0 everywhere, and this one is where it is random for every next spatial component. So both these things have the same spectral contents, but this one is really centered, and that's what we don't want to have. Our system has to be kind of the same everywhere independently where we look at it, and it also has to have this variation. So assuming this kind of form, we can just plug it into two-dimensional pattern for the director and do all the calculations, and then match the experimental scattering pattern with simulated one. And well, I would say this is quite a good agreement. So anyway, good agreement. So now what do we get from that? On the right here, this is the visualization of the director, and color represent the deviation from the average vertical direction. The yellow one is deviation in one direction, the blue one in the other. And well, I hope you can see that the shape of the colored domains changes from the top to bottom, and they get elongated in the vertical direction, that is direction of stretching, and while the variation in the horizontal direction stays more or less the same. This is just a little bit magnified pictures, and I'll probably conclude with saying that light scattering is a useful technique, and it can be used just from practical point to monitor the dynamics of the evolution of the process during the preparation or synthesis of the elastomers. And on the other hand, it could help us understand somewhat the internal structure of the material. And then even assuming really simple, well, as simple system as we can get some nice matching with experimental data, and that also, and the results are consistent with the assumption or statement that there should be some sort of domains of some length scale, and that the shape of those domains changes during stretching of the sample. So now I would be happy to answer questions, but I guess we're out of time. Thank you.